Good afternoon, everyone. I am Tony Robinson with MAP, and welcome to today's webinar titled The Movement Towards Non-Halogenated Flame-Retardant Polymers, presented by Priscilla, Tom, and Chris of Amco. And we are also joined by Maggie of Pinfa NA/FRX Polymers. Just a few notes before we get started. I will be keeping all attendees muted throughout the presentation, but please keep yourself muted as well to eliminate any kind of background noise. And there's no real need to share your cameras either, as this will not be a very interactive webinar. We are recording the webinar and it will be up on our webinar archives page in the next few days. You will need a member login to access that page, so just reach out to us if you need any help with that. There is time for questions at the end of the presentation. Please use the chat feature to ask any questions. And if you have any logistical issues, you can use that chat as well, and I will help you troubleshoot. So with all of that being said, I will turn it over to Priscilla. Oh, Priscilla, you might be muted.
It goes to Chris.
Hey, yeah. Hey, good afternoon, everybody. Thank you for taking time out of your busy day to take part in our seminar on the trends towards non-halogenated flame retardants. And I think you're going to find this information both interesting and useful when you're dealing with FR materials. My name is Chris Lurrell. I am the Amco product manager for basically all things compounding. This topic is near and dear to my heart as my major product line is TriStar polycarbonates. These are flame retardant PCs tailor-made for the E&E and telecommunication markets. I've been in the industry for roughly 30 years, starting my career as a finite element analysis engineer for GE Plastics. I've worked at a couple of major automotive molders in a variety of roles. I joined Ravago as a plastics engineer roughly 18 years ago. Most recently, I was the engineering manager for Amco Polymers. And 4 years ago, I jumped over to the commercial side as a product manager. Presenting today will be Tom Cunningham for the first half. Tom is our R&D engineer. He does all the formulating for our TriStar product line. He's also our liaison to underwriters laboratories. He ensures our product meets all of the UL standards on a yearly basis. Tom has been in the industry for roughly 40 years. Presenting the second half will be Maggie Bauman. She's business manager for FRX Polymers, specializing in non-hal FR additives. She's also the outreach committee chair to Pinfa North America. Thank you, Mag, for being part of this presentation. This is just our standard disclaimer for today's presentation. This covers both the Zoom meeting and I believe the actual presentation, which will be up on the MAP website. Just formality. A little bit about Amco Polymers. We are a full service stocking distributor. We have a network of warehouses around the country and 45 plus sales associates. We tend to pride ourselves in being a solutions driven partner for our valued customers. We have an application development team and as well as process engineers ready to help on a dime. We have what I consider to be one of the broadest and most encompassing line cards in the industry. So with that, I'm going to pass this over to Tom Cunningham.
Good afternoon, everyone. This is Tom Cunningham. As mentioned, I have about 40 years of experience in extrusion compounding and formulation development. This is an introduction discussing what this presentation is about. We are looking at a change in the marketplace with regards to the use of halogens in helping us formulate flame retardant compounds. So many halogens have been identified as a problem in the environment and a health problem and that sort of thing. So we're being asked by government agencies to change over to less harmful materials. That being said, not all halogenated chemicals are harmful. Today we'll be talking about these different subject areas. So Flame retardant polymers are very common in our day-to-day life and the products that we use. Shows the amount of flame retardants that are added into various polymers for the applications that are out there. A lot of flame retardants go into building and construction, electrical applications like wire and cable. We have some pictures of electrical enclosures. As everybody's well aware, we are moving towards electric cars and electrified cars. So there's a lot of requirement for flame retardancy in those applications. And of course, consumer products like printers and computers require flame retardant plastics. One of the fundamental tests to determine the flammability of a polymer is called the limiting oxygen index. And basically, in a fixture like over to the left, a sample of polymers is put in a tube and lit on fire. Then they change the ratio of oxygen to nitrogen to see how much oxygen is required to keep that sample burning. On the right-hand side is a list of various polymers and basically how much oxygen is required to keep that sample burning. So since all the plastics sit in air, the critical point here is 21% oxygen. If you have a polymer that requires more than 21% oxygen to keep burning, generally it'll self-extinguish. Below that 21%, the polymer will keep on burning, causing a problem. Coincidentally, a lot of your commodity polymers, your polyolefins and such have very low LOIs. So they are large presence in the environment, and also they will burn fairly easily. Our material that we're looking at today is polycarbonate, which has the feature of a fairly high LOI, which means that it's easier to make it flame retardant. So we're going to talk a little bit about testing of flame retardant polymers. The LOI is not really used as a standard industry test. It's an indicator. There are some industry tests which are go through someone like UL, Underwriter Laboratories, and get certified. There's a lot of different kinds of flame retardant testing out there, but this is the most common, by far the most commonly performed tests. So the standard at UL is called UL 94, and we submit samples of our products, as do other suppliers, to UL. They run tests internally and determine how flame retardant a particular material is, give it a rating and a certification. So on the column to the left there, you have various ratings like HB, V2, V0, 5VA. As we go down the list, these tests become more and more difficult to pass. The V testing uses a 50-watt flame, as you can see over to the left, which is fairly small. And the 5VB, 5VA testing uses a 500-watt flame. So there's a big difference in the performance of a V-rated material versus a 5V rated material. There's different techniques that are used across the top for these tests that are shown. The most basic rating for flame retardancy is HB, which just basically is similar to the LOI test. It gives a basic idea of how flame retarded a material is. Next slide. So once you've passed some of these tests, you can apply for a yellow card from UL, which is basically the certificate which says that you are certified by UL. There are a number of other properties you can have tested at the same time with your sample to show what kind of physical properties it has to go along with that flame rating. Some suppliers will list their materials as internally tested or expected values. We even do the same thing when we have a developmental material and we're expecting it to pass a UL certification. Maybe it's being test marketed to see if there's actually any interest in the marketplace for the property profile that we've published. And so sometimes you'll see, say, a prospector data sheet internally tested listed, but that does not mean that it has a actual yellow card. So we're going to get into a little bit of discussion about the chemistry that's used, and we can discuss what options are going to happen in the future. So the primary flame retardants that are used are classified as halogen and non-halogens. A halogen compound would contain bromine, chlorine, or fluorine. Bromine, in terms of halogens, in the present is one of the more popular flame retardants. It's very effective as a flame retardant, these bromine compounds. Chlorine compounds have lost favor over the course of time, but they're still used here and there. Fluorine compounds are fairly uncommon in terms of a primary flame retardant as a halogen. A lot of fluorine gets used as PTFE, which is an anti-drip component for flame retardant formulating. In terms of non-halogen materials, the materials that we're going to have to turn to in the future, the biggest volume is minerals of various types, which usually are formulated fairly heavily, and they have various actions as a flame retardant in terms of absorbing heat and releasing water. We also phosphorus compounds are becoming more popular, nitrogen compounds, silicone compounds, which have special reactions with some materials. Also, silicon itself does not burn. And then there are specialty additives for particular polymers that are not universal. Some of these compounds could be in higher molecular weight or even incorporated into the polymer chain. A lot of times these materials are used together and you get a synergistic response. In other words, they work much better in combination than by themselves. So on this page, we have a graphic showing the basics of what happens during a fire or a polymer on fire. There's some terms that are used to explain what's going on. The condensed phase is basically the solid plastic in the area that's decomposing. The gas phases would be the volatiles that are coming off the polymer and the actual combustion that's occurring. Different flame retardants work in different parts of this process in order to limit the burning. The halogens have been known to work up in the combustion where they act as free radical traps. They stop the reaction and have been very effective doing that. The only other material that really acts as a free radical trap a little bit are some of the phosphate compounds. They're not as effective as the halogenated compounds. The other materials, say the minerals, work to displace the polymer, essentially have less polymer to burn. Some of the materials form a char layer, which gets between the flaming area and the condensed phase. And there's a couple other effects such as materials which absorb some of the heat and reduce the flaming. So different materials have different chemical actions, and some of them have different environmental fates. In other words, the problem is they persist in the environment, and so those materials are being moved out, substituted by some materials which are more environmentally favorable. This shows the formulating of flame retardant types, with halogenated being in the first column, showing the brominated, chlorinated, fluorinated materials. They work with antimony trioxide as a synergist. I've made a lot of pounds of compound with this type of formula in the past, and it's very effective. It's very popular, or has been very popular, and will be being phased out in the future. Non-halogen formulas based on phosphates and melamine require more material to go in to the formula. This causes problems with physical properties. You're basically replacing the resin with something that doesn't have the strength of the resin, so you can't maintain the properties of the resin as easily when you're substituting out these materials. Plus, they tend to be more expensive than the base resin. Mineral fillers, which go into a lot of polyolefins and that sort of thing to provide flame retardancy, are used at very high levels. And I don't formulate these compounds, and I'm glad I don't have to, because I believe it's very difficult to try and get a good set of properties and good flame retardancy out of that. The advantage, and it's not on the screen, the advantage of polycarbonate is because of its high LOI, we don't need to put these kind of numbers of amounts of flame retardants into the polycarbonate to get good flame retardancy. So these are the concerns that are occurring right now with the halogenated and some other flame retardant chemistries, and the regulatory efforts that are coming down the pike, which will change formulating in the future. So flame retardant additives are suspected carcinogens, endocrine disruptors, can cause neurological damage. They generate dioxins and furans when they're incinerated, which are very toxic chemicals, and they accumulate in the environment. The accumulation in the environment is something that's been noted in halogenated chemicals for a long period of time. And many of you will recall the problems with DDT, which is a chlorinated halogen, which was used to control mosquitoes in the past. And they found that it was starting to build up in the environment and cause problems with predatory birds, and they were causing thinning of eggs and this sort of thing. Those populations are going down. DDT is controlled a lot more now, even though it's used in some areas, and those birds are, in the last reports I've seen, recovering because of taking the halogenated chemical out of the environment. This graphic shows how quickly things are moving now to restrict the use of certain flame retardants. So between 2000 and 2017, there were a couple regulations put on certain flame retardants, and they were taken out of the marketplace. Materials that I used in great quantities in the past. One was known as DECA, We would use DECA and ammonium trioxide a lot. That was taken out of the marketplace and replaced with some other materials. Now, in the 2022 and 2023, many governments and jurisdictions are passed legislation to limit the use of halogens, and we need to react to that. Everyone needs to react to it, because you won't be able to ship into some of these locations if you don't meet some of their regulations criteria. Beyond government agencies, large technical companies have decided that they want to become better social citizens by using less harmful chemicals or in their products. So they've made announcements such as the one below is kind of a tag that they put on and say, we're not going to use these materials in our products. We don't have to worry about our products. So there's a lot of pressure from the customers. The molders are being told by companies that they want to use safer, more socially responsible products. And we'll get into that a little bit more in a bit. So this is what I mean by getting into it a little bit more. The third-party validation companies or groups are being developed, and certifying agencies are out there to say, hey, our stuff is safe. Our stuff is a good environmental product. Our material is going to be recycled. One of these agencies is known as Green Screen. And this big chart in the bottom is a number of different areas that they look into to make a determination of how safe your material is. At least from their perspective. So they'll give you a score, and then some of our customers have started saying, hey, we want a benchmark 3 material, at least a minimum benchmark 3. So we have to make changes to our product line in order to meet our customer requirements. One of the things that we've done already is to get UL 746 certification, which is a halogen compliant certification on our yellow cards. And we're one of the few companies to have done that so far. So as I've mentioned before, the limiting oxygen index of 27 for polycarbonate is a favorable thing for us. So we can use very small amounts of flame retardants in order to get very high flame retardant ratings, such as 5VA, which is difficult to achieve. Those low amounts of flame retardant additives allow us to maintain our physical properties of the polycarbonate. One of the predominant physical properties is high impact resistance that polycarbonate is known for. Additionally, we're coming out with compounds which are halogen compliant and maintain optical clarity. Let you know that's a difficult thing to do. And a number of the other properties, such as high temperature resistance, mechanical strength, and these things, we're able to maintain in our newer flame retardant non-halogenated formulations. And we'll move the presentation over to Maggie Bauman of Pinfa and FRX.
Okay. Hi, I'm Maggie Bauman. I want to thank you for joining us this afternoon. What I would like to cover initially is a little bit of an introduction to Pinfa. That stands for the Phosphorus, Inorganic, and Nitrogen Flame Retardant Manufacturers Association. By the title, you can see why we've nicknamed it Pinfa, but what it is an organization that's been formed to support education and outreach regarding the various types of FRs available in the non-halogenated space. So we are an organization of member companies. These are producers of flame retardants, formulators like an Amco, and users of PINFRs like the OEM community that Tom referred to. So Pinfa members work on projects to educate and also support fire safety. We get involved with the supply chain regarding how you can more effectively work with non-halogenated flame retardant additives. We actively communicate with regulatory and non-government organizations, nicknamed NGOs, and third-party certification organizations that Tom referred to, like Green Screen or Chem Forward or EPEAT, or any of those that are in the space of kind of evaluating brands as to whether they meet these more challenging EHS requirements. Some of the services we offer that are free, often free anyway, our newsletter is an excellent regular monthly edition that covers developments in flame retardants, regulatory, product development, and application information. We also offer webinars. We offered a webinar earlier today on testing, fire testing. And we develop market brochures that focus on the major industries that consume flame retardants: building, construction, electrical, electronic, and transportation. Of course, it's in other markets to an extent, but these are by far the biggest markets, as was demonstrated in that slide that Tom had earlier about the 2021 consumption of flame retardants. We also get involved as much as we can in other organization activities, conferences, and trade shows. And this allows us to have regular exposure to the supply chain and end users in our areas of expertise. The logos on this slide indicate the member companies that are supporting and advancing Pinfa in the marketplace. Next slide, please. Okay, yeah, thank you. In this case, building on all the things Tom talked about, I thought I would just do a quick chart on what's happening in flame retardants overall. Tom mentioned the regulatory movement and brand owner preference to move away from halogenated materials. So what this slide basically depicts that, moving from smaller molecules, whether they're phosphorus or halogen based, toward halogen-free, larger molecular weight, phosphorus-based and nitrogen-based flame retardants, as well as the mineral families, which are also very benign. So this slide basically would indicate that the direction product development in flame retardant additives should go would be toward polymeric, non-halogenated, and reactive moieties. Next slide, please. Okay, so the reason why I was invited to speak is that FRX Polymers, which introduced into the marketplace in 2007 a polyphosphonate. Polyphosphonate is an example of a polymeric, non-halogenated, phosphorus-containing flame retardant additive. In the FRX product line, there are 3 types of materials, all the same, more or less same chemistry, but different forms. The Nofia homopolymers are basically have about 10.5% phosphorus in them, various molecular weights, and has a TG of 105 degrees C. The Nofia copolymers are copolymers of phosphonate and carbonate. And so they look like polycarbonate and perform similarly to polycarbonate in some of the applications that they're used in, whether they're used as a copolymer or as part of a blend or an additive in another, and a polycarbonate in particular is our main polymer we go into with these copolymers. The oligomers are lower molecular weight. They're often, they're either reactive or additive. The functionality is hydroxyl, and they are used in a variety of thermoset applications. Next slide. And this is just a table that compares the different materials, the homopolymers and the copolymers, because those are the ones that we're primarily talking about today. And we just highlighted some of the key properties. This is the transparent material with a light transmission of 88%, not very different from polycarbonate. It has a TG of 105 degrees C, which is a high TG for a flame retardant additive. And then the copolymer that's used as a blend in polycarbonate applications is a higher TG, 121 degrees C. The material also has very good thermal decomposition level, well over 400 degrees C before you see any loss of molecular weight. So those are the key characteristics. Otherwise, it's melt viscosity rates based on molecular weight. So I would like to just highlight a few of the applications that actually a polymeric non-halogenated flame retardant enabled. These are primarily extrusion applications. So the first category is transportation sheet. This is used in mass transportation, for example, aviation and high-speed trains. These materials are halogen-free solutions. The typical solution available today is halogen-based. You need to be halogen-free to pass some of these more stringent smoke or toxicity requirements of the smoke testing. Structural panels, these are largely PET-based. They've gone in to actually replace PVC in foamed insulation applications for metal replacement and PVC replacement in mass transportation. Meets a stringent building construction requirements. It's lighter weight and has good heat resistance. Biaxially-oriented PET film, which has been around for a long time, is to attain a flame retardant clear product is very difficult. With the use of no-fia homopolymer, you can achieve that. Now, the significant uses for the subject today are primarily the products that go through compounders. So these are PCABS, PCASA, PC blends, and we're involved in a number of applications there, primarily in electronic enclosures, but some of these are for medical equipment, auto interior parts, and battery housings. What we can perform here is in a higher heat distortion temperature, and we have good glow wire ignition temperature performance. Good processing characteristics, and we can achieve 0 down to 0.8 millimeters in these types of applications. PETG and RPET, that's PETG, it's glycol PET, and recycled PET in consumer applications, housings primarily, but in components as well. And here we can offer good balance of mechanical properties and post-consumer recycle levels can be increased. In PC, we work well in virgin and recycle applications. These are largely sheet and film applications, but we have been introduced into molding compounds for consumer electronic applications, and that's a recent initiative, and that also incorporates recycled content. We can maintain transparency, and we can achieve V0 down to as low as 0.8 millimeters. So the latest information I can share is what we've done in the 2022 to 2023. We developed a new product. It's called no-fia Co 6010EX. It has improved color over our reactor product and therefore specifically targeted at high color requirement applications like white pigmented sheet and molded articles. It is also, because of the improved color, has a good transparency as well. It's significantly lower yellowness index than our existing product that we make in the reactor. We also have starting formulations for replacement of the fluorinated salts that have been used in polycarbonate. They're called RIMAR. And therefore we're actually very excited about this because of the recent announcements of moving away from PFAs as rapidly as possible. Here, CO 6000 and Nofia CO 6010EX have been demonstrated in formulations for 0.8 and 1.6 millimeter V0 applications. And in some cases, we include a CoFR phosphazine to help balance cost and performance. In our PC blend applications, specifically PCABS, we've been able to demonstrate an enhanced heat distortion temperature by as much as 30 degrees C, and we are V0 down to 0.8 millimeters. So thank you.
Hey, Maggie, thank you. Thank you for all that information. Tom, thank you for your section of the presentation. I'm going to go into a few slides on TriStar, what we're doing to get away from brominated flame retardants, halogenated flame retardants. So we do have a line of halogenated flame retardants, and I have to say right now in the North American industry, they are still the predominant use of type of flame retardants. But as we're seeing in Europe, people are wanting to get away from the halogenated and go to halogen compliant or halogen free. So we have kept up with what they're doing in Europe, and we have a line of halogen compliant flame retardant polycarbonates. These have the full UL yellow cards of V0, 5EA options, 5EA at 2.5 millimeters, glow wire F1 approvals. So they've been subjected to both UV and water immersions and still maintain their flammability. We have the full line of elevated RTIs. So what does that mean? So if you look over to the yellow card on the left, RTI for electric impact and strength, you can see that is 125C, 115C, 125C. So our products can maintain 50% of their property for strength, your tensile strength, after being subjected to 125 degrees Celsius for, I believe, a duration of 3,000 hours. If you looked at most polycarbonate yellow cards out there, you're going to see values between 65, 80, 85 degrees C. Just want to mention ours have the fully elevated RTIs, which is very important to the E&E, the telecommunications markets. We have options that have improved impact resistance at low temperatures, improved chemical resistance. We can manufacture TriStar not only in North America, but China and Europe as well. Next slide. This is just I won't go through this whole slide. This is just our halogen compliance series. We have options going from V2 all the way down to 5VA at 2.5 millimeters. Glass options available. Always custom colors, clears, naturals. Impact starting at 12, but going up from there depending if we put impact modifications in it. Melt flows all the way up to roughly 20. Just want to say a little bit more about TriStar, versatility. We can make custom products all the way down to 55 pounds. Of course, most of our stuff is shipped in 1,500 pound kilos, but we do truckload shipments, bulk trucks. Color match time is typically 1 to 2 weeks. Our lead times right now are 3 to 4 weeks on custom made to order products. We also have roughly 25 products that we consider stock grades that are stocked around the country. Just going back to the past couple of years during the pandemic, during all the supply chain issues that were out there, the lack of base polymers, coloring issues, white color went pretty scarce there for a while. There's 6 months when glass fibers were very short. There was a time when we couldn't even get cardboard boxes for a while because Amazon had cornered the market on cardboard. I just want to say we did not shut anybody down. We didn't put anybody on allocation. We were able to maintain consistent supply for our customers. Next, I just want to go in a few slides on some new products we have developed, both in brominated, halogenated, and halogen compliant series. So when you look at extrusion, polycarbonate's not like polyethylene where you can get frac melts. Polycarbonate pretty much bottoms out about 2.5 on your MFI when you're looking at branch materials. So if I were to take that and to compound flame retardants in it, the active compounding is going to add roughly 2 to 3 to the melt flow. Flame retardants actually increase your melt flow as well, so that could add another 1 to 2. Tom has done a lot of work, and we've been able to come back with a 5VA product, halogen compliant, that has a melt flow between 4 and 6. So very excited about the launch of this product. Next slide. We also very close to launching a transparent 5VA product out there. There are a few grades out there right now from some of the major suppliers. Right now, we can achieve V0 at 3 millimeters, but we're going to be launching soon 5VA at 3 millimeters. Still flight transmission around 88% and haze less than 1%, halogen compliant version. Excited about this one. I think we'll be able to offer some cost saves versus what you're seeing in the market today. Hydrolysis resistance. Roughly a year and a half ago, 2 years ago, we were challenged by one of our major customers to improve the hydrolysis resistance of polycarbonate. They mold a box that is used all around the world, but in typically when you get towards the Tropic of Capricorn and Cancer, those areas tend to be high humidity, high temperature, and they were seeing some failures in the material that they were currently using. So we developed version 1.0, where we were able to pass their test, where they took the parts for 2 weeks, they put them under 85 degrees C, 85% relative humidity, and then tested several of the material properties after that, and determined with our version 1.0, we didn't see any degradation of properties. Since then, Tom has formulated what I call version 2.0, and we're currently testing it up to 3,000 hours, and right now we're not seeing any degradation of the properties. Again, when you had bit conditioned to 85 degrees relative humidity and 85 degrees Celsius in temperature. Last, I believe, we developed a new low temperature impact grade where we're seeing roughly a 7 ISOT at negative 40 degrees C, which is typically polycarbonate. It's going to be around a 2 or 3 at that point. This is with using impact modifications, not using a copolymer where you're putting siloxane in and coupling it with that, because siloxane is rather expensive. This is just our standard type products with just a little bit of enhanced impact modification. We can get that ISOT up to 7 at negative 40 degrees C. So with that, I just want to do a quick overview. You can see there are many applications where plastics need to be flame retardant for safe usage. If you look outside on a telephone pole, you might see a gray box up there. Those need to be V0 at 3 millimeters. If that box is on your house, telecommunications box, and that has to be 5VA at 3 millimeters. We're also starting to see when you're looking into the automotive market, what we call e-mobility, looking at electric vehicles. There's a whole new slew of requirements going for flame retardants in that market, which is primed for polycarbonate, because now you're not dealing with an internal combustion engine and all the fluids and oils that are associated with that product. Now you're into a battery situation, which has its own different kind of chemical resistance needs. So we're discovering polycarbonate is a prime opportunity, prime material for that market. Many of the flame retardants that you've seen in the past, they found to generate some EHS concerns, which is environmental health safety. So we've been moving with the industry. We've been moving with Europe to move away from halogenated products into HCs, which is basically what this whole presentation was about. So new flame retardant plastic compounds are being developed to address these emerging markets. For us, that's our HC series of grades, and we're also looking at doing some other different kind of flame retardants that you've seen in this presentation. Polycarbonate, because of its good limited oxygen index properties, is a great polymer for FR products. You can go to there are other products out there like PEI or PPS that have even higher LOI numbers, but when you look at those products, you're going to see a factor of 2, 3, or 4x in terms of cost. Polycarbonate uses very little flame retardant. It's being inherently flame retardant, uses just a little bit of flame retardant to make it 5DA, and it still maintains its properties, dimensional stability, impact, UV resistance, great creep properties, and it's relatively easy to process. So with that, I think that's the end of our presentation. I will open it up to questions. Thank you, everybody. Thank you for taking time today and listening to what we have to inform you about flame retardants.
All right. Yes. Thank you for that presentation. We did get some questions sent directly to me in the chat. So what are the main markets that are demanding a movement to more sustainable solutions? Maggie, maybe you can answer this one. You're muted.
Thank you. I'm sorry. I did mute myself so I would be polite. Any market that has consumer contact is looking at improving its sustainability profile. And so, for example, consumer electronic applications. We mentioned electric vehicles. There's a lot of electronics in electric vehicles or in conventional internal combustion engine vehicles. That's an increasing application area. And the other area would be building materials that actually are, in touch with the environment. So any of those areas, coupled with that is the desire to use more recycled content. And so that those are the applications that are demanding better additives as well, including flame retardants.
Okay. The next question that I got, what are the largest applications for Amco FRPC?
Chris, I can take that one. So I'm assuming you mean my markets. So, as I stated, the E&E market, telecommunications, and e-mobility, the electric car market is we're releasing a lot of traction for FRPCs. Also building construction too. You definitely seeing things within the solar panel markets going to flame retardant PC as well.
Perfect. I really like this next question. How is the market changing in North America as opposed to the EU?
I can take that since that's kind of a Pinfa thing too. In Europe has always been the lead on the move to more, let's call it EHS, environmental health and safety. And it has been the first market to really adopt non-halogenated flame retardants in a large way. In fact, that's why some of the producers that are active globally are actually European producers. A large quantity of them are. But what has happened is that we don't have applications that are regional as much as we have in the past. Things are typically more global. So you see a product developed in one region, produced in another, but then consumed in any of the regions. So that was already happening. What's happened since the first of 2022, the first day of 2022, we've had 4 to 5 states in the US and Canada start to adopt programs, regulations regarding products sold within their states, primarily focused initially on consumer applications, electronic displays and the like, to move away from halogenated flame retardants. And now it's on a state-by-state basis, but 2 of those states are very large population states, and these are states that typically lead in environmental initiatives anyway. So other states are beginning to look at that legislation and are actively considering it.
Okay. Thank you, Maggie, for that answer. What about BPA? Chris, could you possibly get this one?
Yes. I'm assuming you mean BPA and polycarbonates. BPA is part of polycarbonate. So when you make polycarbonate, you use a process called condensation polymerization. So you're taking BPA and you're combining it essentially with carbonyl chloride. When you do that, you create polycarbonate with a byproduct of hydrogen chloride. So BPA is present in polycarbonates. For my product line, we're not really selling into, I guess, housewares or the consumer good market. So you're not going to make a flame retardant baby bottle or flame retardant glassware. So flame retardants and those type of products are really an issue. So the BPA portion in the E&E market, telecommunications, I believe is not really a concern.
Okay, I did just
I
get
answered that
another
question satisfactory to whoever asked that.
Yeah, we just got another question in the chat as well. Will flame retardants change within a product designation such as PC10FR, or would I need to switch to a different designation to use a more environmentally friendly flame retardant? Has UL implications for those with designations written into their own file? I'm not sure who would like to take this one.
I can take that one. This is Tom Cunningham. So when we develop a halogen compliant version, we get a different yellow card for that product. So it will be listed something like PC-10FRN-HC. So it's basically UL does not allow for a change in your chemistry for a named product over the course of time. So we have to apply for a different yellow card with the change of chemistry.
So I'll just add a couple more comments to that. We do have roughly 26 yellow cards within this TriStar product line, both for the halogenated and the halogen compliance, different formulation versions. So when you work with us, we will always send you the appropriate yellow card that is applied to the grade, which can be confusing at times. But moving forward, we always looking to develop new products and work with UL to develop more. I just want to make one other comment. When you're looking at the fully F1 rated elevated RTIs, they tend to be expensive to get the UL certification, but not only that, it takes roughly a year to go through all the testing.
All right, I'm not seeing any other questions come through, so I'd like to thank Amco Polymers and Maggie as well for offering the information today. Just a reminder to the attendees, the recording will be posted by the end of the week. So thank you to all of the attendees for being here, and I will now end the webinar. Everyone have a great day.
Thank you.
Thank you, everybody.